Welcome back, dear students, to this new lesson on the chapter Computer Organization and Architecture. For the new members in the Byte family, you are all welcome to this channel where we are breaking down all the chapters of Advanced Level Computer Science 795 as and A-Level ICT 796 as well. Okay, today under the chapter, we are going to look at parallelism. Let us proceed. Parallelism. This is the execution of multiple instructions or tasks by using multiple processors or processing unit at the same time in parallel, or called parallelism. Execution of multiple instruction or task using multiple processors or processing unit at the same time and in parallel. Parallelism greatly increases the performance of computers. It can be achieved through parallel processing or pipelining. So the two ways by which a computer can perform parallelism is either through parallel processing or through pipelining. Let us look at the first one, parallel processing. Parallel processing is the use of multiple and independent processors. So the processors we are using, they are not dependent on each other, they are independent of multiple independent processors simultaneously to execute a single program or task. The problem is divided into portions so that multiple processors work on the assigned portions of the problem at the same time. That is how parallel processing works. Parallel processing requires special software that recognizes how to divide tasks and then bring the result back together again. Some PC implement parallel processing with multi-processors while others have multi-core processors. So there's a difference between multi-processors and multi-core processors. Let us look at them. Multi-core processors. A CPU can contain one or more processing unit, which is a core, because a core is what we call a processing unit. A core is a complete independent processing unit inside a CPU chip that can fetch, decode, execute, and complete instructions on its own. It contains a control unit, arithmetic logic unit, and a register. So that's the definition of a core. It is common for computers to have two, four, or eight, or even more cores. So when a computer has two cores, we call it a dual core. When it is four, it's a quad core, and if it is eight, it's an octo core. It's an octo core. So that's how it is being given. So sometimes you hear advertisement about computer, they say it is a dual core, it's a quad core. You already know the meaning. CPUs with multiple cores have more power to run multiple programs at the same time. So that's what we mean. So when we have a dual core computer, two cores, it means that it has the capacity of running multiple programs at the same time. But note, a dual core computer, which is a PC with two cores, can execute two different threads or two parts of a program at the same time. The same thing with quad core, four different threads executed simultaneously in parallel. So when you have a computer which is dual core, it simply means it can execute two different threads, that is two different tasks at the same time, or it can execute two different parts of a same program at the same time. In case it is a monocore for one computer, one core, then it's going to finish with one part of a program before taking the other part, whereas a dual core can handle the two parts at the same time. And in case it is four parts and we have a quad core, each core can be assigned one thread to execute the task in parallel. More core is not always better for everything. E.g., basic office work or web browsing are perfectly fine on dual core machines. What do we mean by here? Having an octo-core or a quad-core to perform the functions that a dual core can perform very well, like basic office work or web programming, will not increase the will not reduce the processing time. No, the cores here are simply independent unit. It is just like you have a particular task that can be managed by two person, but you assign four person. In this logic, it is true that the task will be executed faster, but having two cores meaning that what? The two cores execute the work for which they will be assigned perfectly well, and a quad core will simply assign just two of its cores, whereas the two others will remain idle. So in some cases, having more cores is not always better. Another point is that a dual core does not automatically mean twice as fast. Take note, a dual core does not mean that the computer is twice as fast. No, it simply means that each core, and it simply means that the computer can execute two threads at the same time. Now, why do we say dual core does not automatically mean twice as fast? CPU cores have to communicate with each other through channels, and this uses up some of the extra speed also. So the communication that the cores takes in communicating, it increases the speed. Also, if a program is not multi-threaded, that is conceived to use multi-core, because there are some programs that are conceived in such a way that it cannot be broken down and can be managed only by one core, then it will run with a single core, which is not different from when a monocore executed. That it brings us back to this level. And mini-core is not always better for everything. So if you have a task which was programmed to be managed by only one core, then having 8 core will not increase will not reduce the time for processing, because it has been conceived to use one core, and a computer having 8 core will be making use of one of its core only. Multiprocessors. Let us look at multiprocessors now. Computer system may contain many processors, each possibly containing multiple cores. Such systems are called multiprocessors. So you're having a computer that has more than a single processor. Whereas multi-core, you have just one processor, but it contains several units. This system either executes a number of different application tasks in parallel, or they execute subtasks of a single large task in parallel. All processors usually have access to all the memory in such system, and the term shared memory processor is often used to make this clear. So for multiprocessors, they have access to a common memory, which is mostly termed shared memory multiprocessor. The high performance of this system comes with much higher complexity and cost. So to have a multiprocessor machine, it is costly, and the complexity of such system is equally high. Now, let us look at pipeline processing. When an instruction is executed, it is first fetched, then decoded, then executed, and finally the result is written into place, meaning that it is stored. We are going to go deeper into this when we shall be looking at the instruction cycle. Now, so these are the four principal stages, although the last one is not really necessary. These are the different stages that are put in place or that must be done when an instruction is executed. With this scheme, a simple processing unit takes 4 cycles per instruction, as you can see. So if I have 3 instructions, instruction 1, during the first cycle, he fetches. During the second cycle, he decodes. Third cycle, execute. Fourth cycle, he writes the result. Then the second instruction does the same thing from clock cycle number 5 to clock cycle number 8. And the third one does the same thing from clock cycle number 9 to clock cycle number 12. So for the processor to execute 3 instructions, he's going to use 12 clock cycles. Now, what can we realize here? If we overlap the execution of the steps of successive instruction, the total time will be reduced. What do we mean here? That is, at the same time I am performing decoding for instruction 1, at the same time I am performing the fetching for instruction 2, because I cannot fetch 2 instructions at the same time. Remember, stored program concept, everything is done sequentially. Now, the total execution time will reduce in case I overlap the execution of the steps of successive instructions. That is, the next instruction could be fetched from memory at the same time the current instruction is being decoded. This form of parallelism is called pipeline processing. Let us understand what we mean by that. Pipeline processing, commonly known as pipelining, is an implementation technique whereby multiple instructions are overlapped in execution. Now, this is the instruction flow in a sequential processor, as you can see, what we just from seeing, 3 cycles, 3 instructions, sorry, consuming 12 clock cycles. If we decide to overlap, this is what we are going to have. So this is the instruction flow in a pipeline processor. At the first clock cycle, I am fetching instruction 1. At the second clock cycle, I am fetching instruction 2 while I am decoding instruction 3. At the third clock cycle, I am fetching instruction 3 while I am decoding instruction 2 while instruction 1 is being executed. During the fourth one, as I'm decoding instruction 3, I execute instruction 2 and I write back instruction 1. At number 5, I execute instruction 3, I write instruction 2, while instruction 1 is already done at clock cycle number 4. Then number 6, I simply write instruction 3. So you see that when I overlap this series of steps, I am consuming only 6 clock cycle, which is practically half of the amount of clock cycle I'm using when I'm executing them sequentially using a sequential processor, as you can see. Now, you clearly see that in a pipeline processing, the clock cycle reduces, meaning that what the amount of time we take in execution reduces, which is something beneficial. Different instructions are processed simultaneously at various stages, similar to an assembly line. This increases instruction throughput, that is the number of instructions executed per second, because remember, the throughput is the number of instructions divided by the clock cycle, that is the amount of time. At this level, I have 3 instructions. When I take 3 divided by 12, it gives me 1 quarter. Whereas here, when I take 3 instructions divided by 6, it gives me half. So instead, the throughput has increased because half is above 1 quarter. So this increases the instruction throughput and reduces idle time in the processor, as you can see. Because clock cycle, look at the clock cycle number 3 here, for example. So it's at the time it takes in performing the fetching of instruction 3, the decoding of instruction 2, and the execution of instruction 1 is the same time that is being allocated to perform just one instruction here. So after performing this writing of instruction 1, the amount of time left is being idle. That's why we say it does not only pipelining does not only increases the throughput of instruction, it also reduces the idle time of the processor. Pipeline improves throughput instruction per second, not the latency of a single instruction. Exercise. I think this is the first exercise we have for this chapter. Center Regional Mock 2023, question 1 sub 2b. Question came just for 3 marks, but it is very important. In a RISC processor, 3 instructions A followed by B followed by C are processed using pipelining. The following table shows the 5 stages that occur when instructions are fetched and executed. The A in the table indicates that the instruction A has been fetched in time interval 1. Each time interval represents 1 clock cycle. Copy and complete the table to show the time interval in which each stage of each instruction ABC is carried out. Hence, calculate how many clock cycles are saved by the use of pipeline in the above example. So you are using a pipeline instead of because it's precise. Are processed using pipelining. So you need to complete. A here means that what instruction A is being fetched. So at clock speed number 1, A is fetched. So what happens? So complete the table, assuming that the 3 instructions A, B, and C. So if you put, for example, C here, it means that C is being decoded. If here you come and put B, it means that this level B is being the result is being written. The result of the execution of B is written to the register, and you are being asked to calculate how many clock cycles are saved by the use of pipelining. How many are saved? Let me just take an example here. In a sequential processor, I had 12 clock cycles, while in a pipeline, I had 6. So the number of clock cycles that are saved is equal to 12 minus 6. And also, the number of clock cycles we have in a sequential processor is equal to the number of instructions times the number of clock cycle per execution of an instruction. So I think I gave you much hint about the question. The solution will be given during the weekend in the WhatsApp channel. Thank you and see you in the next video where we shall be, as you can see, we shall be looking at the RISC and the CISC machines. Take note that the fact that you don't have an idea about RISC and CISC machines as presented in this question does not deprive you from answering this question correctly. Do not forget to like, to subscribe, and to share for our community to grow. Thanks and see you in the next video.